In this video lesson, we are going to learn about a special class of differential equations called separable differential equations and some techniques for solving them. Separable differential equations are equations that you can separate into two sides, one with only x's and dx's, and one with y's and dy's. So, example one here. This is a differential equation, and I think that it's possible to rearrange this equation so that only y's and dy's are on one side, namely the left side, and x's and dx's are on the right side. Moreover, that the dx's are, that all these operators, the dx and the dy, are in the numerators. It's not 1 over, like in the case how this is starting here. So this is not so bad. dy's are already on the top on the left-hand side, so that's where I'm going to start. I'm going to try to get the y's on the left and the x's on the right. So let's see, to do that, I'm going to add, I'm going to add 1 to both sides of this equation. That gives me 2x and then dy dx, and that's y squared plus 1. And let's see. I need to get this dx out of the denominator here, so I think I should multiply both sides by dx, which is going to force, if I multiply both sides by dx, that'll get rid of this dx down here, but I have the y operator on the left, but expression with x's, and then an x operator on the right with an expression y's. I don't want that. I want y's and x's. So this is not so bad. I'm just going to divide by this expression, y squared plus 1 on both sides, and then divide by 2x on both sides, which is going to have this effect. I'll have this term, 1 over y squared plus 1 dy on the left-hand side now, and on the right-hand side will be a 1 over 2x and a dx operator. Now I've got this equation separated into the y expressions and the x expressions. To undo these operators, well, this is easy way to do that, is to undo a differential is to integrate. So I'm going to, oh, that's a terrible integration symbol, but I'm going to integrate both sides here, and the integration will undo this differential operator, and we will have an expression without the operators, and then in the end we'll try to rearrange this equation to solve for y. Additionally, we have an initial point. We're going to find the particular solution to this, meaning when we get this constant of integration, I'm going to substitute in 1, 1, and eliminate the plus c that we're going to get. So in any event, let's see, the antiderivative of 1 over y squared plus 1 is arctangent. So this is arctan of y. The antiderivative of 1 over 2x is 1/2 of the natural log of x, and then plus some constant of integration. Note that you might think, why isn't there a plus c on the left-hand side? There could be, but I'm going to just lump them all together. Whatever this constant would be, I'll subtract it and just kind of lump it together in one standard constant of integration on the right-hand side. Next, I can take the tangent of both sides, and that would be a perfectly fine step. Before I do that, though, I'm going to figure out what this constant of integration is, because I know what this initial condition is. I know that the point 1, 1 is on this thing, so I'm going to figure out what c is first before I go doing the tangent, because it'll be just a little bit easier to work out. So I know that the point 1, 1 is on there, or mainly that this condition is true. The arctan 1 is equal to 1/2 of the natural log of 1 plus c. See, arctan of 1 is pi over 4. The natural log of 1 is 0. So this tells me that c is pi over 4. So since the arctan of y is now equal to 1/2 the natural log of x plus pi over 4. I can rearrange this equation, or better yet, I can take the tangent of both sides to get y by itself, which tells me that the solution to this differential equation is this form. Is the y is equal to the tangent of 1/2 the natural log of x plus pi over 4. Let's now let's look at a second example. This example is 2 parts. First part, we're going to show this identity, and then somehow we're going to use this identity to try to solve this differential equation. Part A is pretty straightforward. How can I show this relation? Well, I'm gonna cheat. I'm gonna show that the right-hand side, when I subtract them, I get the left-hand side. And that's pretty straightforward. Get a common denominator. I think I should just multiply these two expressions together. So ends up being x plus 1 minus x minus 1 all over x minus 1 times x plus 1, which is x squared minus 1. X minus x is 0. 1 minus negative 1 is 2. 2 on top, and what do you know? X squared minus 1 on top, on bottom. Okay, so this is a multi-part problem, so let's keep in the back of our mind that this is going to come in handy. This to me looks like it's separable. I look at this and immediately see that I can factor a y out. So I see this as right over here. This to me is y and then x squared plus 1 on top, and then x squared minus 1 on bottom. So if I want to separate out the x's and the y's, this is not so bad. I'll just divide both sides by y and multiply both sides by dx. And I'm going to end up with the following expression. I think I can rearrange and separate the variables here to get 1 over y dy. And this is equal to x squared plus 1 over x squared minus 1 dx. As with before, my strategy, I'm going to undo these differential operators. I'm going to integrate both sides. The immediate problem is that this expression is not exactly straightforward to integrate. 1 over y is easy, natural log. But this is not a u substitution. This is rough. However, we did start with part A. Maybe this will be of some use, in that for some reason it looks like this has somewhat of the structure of part A, in that the denominator is x squared minus 1 of both, but this is a 2, and this doesn't have any 2's in it. However, we can force a 2 to be in here. If I just added 1 to this one, to this expression, I'd have a 2. The problem is if I just add 1, that's not really keeping things in balance. There is a trick. We've seen this trick in previous proofs. Instead of adding 1, I'm going to add 0, and I'm going to add 0 creatively. I'm going to add negative 1 and positive 1. So I've just plopped in a negative minus 1 plus 1 in the numerator here. So note that minus 1 plus 1 is 0. So I've not changed the value of the numerator, but I've just changed how it looks. And by doing so, note that I don't have to add in this fashion. I could instead add the plus 1 to get 2. What do you know? And then I'll be left over with an x squared minus 1. But that actually is really nice, because this gives me this expression, x squared minus 1 plus 2 over x squared minus 1. I could take this expression now and separate it into x squared minus 1 over x squared minus 1 plus 2 over x squared minus 1. And x squared minus 1 over x squared minus 1 is just 1. It's constantly 1. So I'm left with, by this nice little trick in, again, noticing this trick from the by being led to it by part A is where we got to. So I think this is the same as x squared minus 1 over x squared minus 1 is 1 plus 2 over x squared minus 1. And what do you know? We know how to, by the previous part, we know that this is equal to this. And each of these individually are easy to integrate. So let's do it. 1 over y dy, we'll take this integral, is equal to the integral of 1 plus 1 over x minus 1 minus 1 over x plus 1 dx, or the natural log of y is equal to x plus natural log of x minus 1 minus the natural log of x plus 1 plus a constant of integration. These we can combine together with logarithm rules and get natural log of x minus 1 divided by natural log of x plus 1. And to get this y out of this natural log, I'm going to raise everything to, I'm going to think of all of this as an exponent of e. E to the natural log of y is y. E to the natural log of all of this mess, well, let's do some combining. This again, we can combine it to one natural log. When we add exponents, that's like multiplying bases. So I claim that the right-hand side is really this. And I'm going to move this constant of integration all the way to the front because that's where constants usually go. So this is like e to the c times e to the x times e to the, well, natural log of this quotient of x minus 1 over x plus 1. Again, I'm using the property of logarithms to combine these together. So let's see. Let's clean this up just a bit, and this will be good to go. A common substitution that you're going to see this a lot in solving differential equations is e to a constant. This is itself a constant, and the standard notation for e to a constant, for whatever reason, is just a capital letter. And usually the Hayes textbook uses capital A, and that's what math professors I've had in undergrad and graduate school use as well. So we're going to turn this e to the c as just some constant of integration called capital A. E to the x is just e to the x, and then e to the natural log of something are, since they're inverse functions, will undo each other. So therefore, I think our final solution here, y is equal to some constant times e to the x times the natural log of x minus 1 over x plus 1. Lastly, for this video, here's another example. It doesn't on its face look like a differential equation, but I claim it is. I'd like to understand what this description is telling us. Just try to draw a sketch a picture, and we'll use that picture to attempt to solve this problem. And we're going to eventually get a differential equation that's actually pretty easy and pretty straightforward to solve. It's very difficult without a picture, though. So I'm going to sketch a curve in the first quadrant. I don't know what this curve looks like. I do know the axes should be more vertical than not. So we sketch some axes. Some curve. I don't know what this curve looks like. I'm going to just use my standard boring curve. It almost certainly does not look like this. In fact, when we're done, we'll be able to get a more accurate sketch of what this would have looked like. But I do know there's a point P somewhere on this sketch, on this curve. Maybe P is here. I do know the tangent of this curve that goes through P intersects the x-axis at a point called Q. So I'm going to draw a tangent line here. I do know this point is Q. The origin is O. And more so, what do I know about this point? I know that this kind of curves, this tangent intersects because of just the way this curve is drawn, but it's tangent locally at this point. What more do we know? We know that for every p on this curve, we know that this is true, that the distance from the origin to p, oh boy, the distance from the origin to p is the same as the distance from p to q, which means that these two segments are the same length. So what does that tell us? Well, let's see if we can come up with some coordinates here. I know that the origin is 0, 0. I don't know what the coordinates of p are, but I can give them a symbol. How about just x and y? I don't know anything more than that. I do know that the y coordinate of q is 0. And based on this picture, I can actually tell what the x coordinate is. Because of the geometry of this problem, if I look at the x-axis, this OP and PQ, this is an isosceles triangle. And what that tells me is that an isosceles triangle, if I draw an altitude from its vertex, that this point here would be x comma 0. And this altitude is a line of symmetry for this triangle, meaning that if the distance from O to directly underneath of P is x, then it's the same distance out, or meaning that this coordinate is got to be twice as far out, or 2x. That's fine, but we still don't have a differential equation out of this. I do know that the derivative of a function, of whatever this function, of this original curve that I started, its derivative is the slope of the tangent line. And what do you know? I have a tangent line drawn in. And its slope, which is the derivative of this original function, I can calculate because I know two expressions for points that are always on this curve, x comma y and 2x comma 0. So last I checked, rise over run tells me that the expression for the slope of this tangent line is always, how about 0 minus y over 2x minus x, which is negative y over x. So a differential equation for this line, for this original curve, is the following: is dy dx equals minus y over x, because the slope of the tangent of every point along this is always minus y over x, because of the condition of the curve being having this property. So we can solve this. This is separable. I'm going to separate the x's and y's. I'm going to divide by y and multiply by dx and get the following. I'm going to get 1 over y dy equals minus 1 over x dx. I'll integrate both sides to undo these operators, and I get the natural log of y is equal to minus the natural log of x plus c. Minus natural log is like minus 1 times the natural log. Note the property of logs, minus 1 times the natural log, or any constant times a log, I can bring that constant inside and make it an exponent. So this is really the same as natural log of x to the minus 1, which is the same as natural log of 1 over x. So again, by trick to get this value of y, to get y by itself, undo this natural log operator. I'm going to do e, raise everything to as an exponent of e, and simplify. And that gets me y is equal to e to the natural log of 1 over x plus c, which is e to the c times e to the natural log of 1 over x. Or using our notation from before, this is y equals a times 1 over x. This is the general solution. So I'm going to plug in 1, 4 to find a, and then I'll be done with this example. So y is 4, x is 1, a, what do you know, is 4. So the particular solution for a curve of this type, where the where the distance from the origin to the point, same as the distance from the point of tangency to the x-axis, is the following: y equals 4 over x.